Hello and welcome to session 3. The topic of today's discussion is acid and bases. The buffer part we will be seeing into the next session. An acidic solution has high concentration of H plus ions greater than that of the pure water, and a basic solution has a lower hydrogen ion concentration less than that of the pure water. And this is about the autoionization of water which occurs in the pure molecule, pure water, where uh, hydrogen ions are spontaneously generated in pure water by the dissociation of small percentage of water molecules. So now the question is, how many water molecules in a pitcher of uh, water will actually dissociate? The concentration of hydrogen ions produced by dissociation in pure water is 1 into 10 raised to minus 7 moles per liter of water, and this equation is very important for the formation of the pH scale. Although the number of hydrogen ions in a liter of pure water is larger on the scale of what we usually think about in quadrillions, the number of total water molecules in a liter dissociated and undissociated is about such a large number. The hydronium ion, the proton does not actually exist in aqueous solution as bare H plus ion. The proton exists as the hydronium ion, that is H3O plus. Consider the acid base reaction. HCO3 plus H2O gives rise to H3O plus plus CO3 minus. Here water acts as a base, producing the hydronium ion as its conjugate acid. For simplicity, we often just write the reaction as HCO3 minus H plus plus CO3 2 minus. The conjugate acid-base pair. Generalized acid-base reaction is Ha plus B gives rise to A plus Hb, as A is the conjugate base of Ha and Hb is the conjugate acid of B. More simply, Ha is A minus plus H plus. Ha is the conjugate acid and A minus is the conjugate base. The amphoteric property. Now consider the acid-base reaction. NH3 plus NH3 plus H2O gives rise to NH4 plus OH minus. In this case, water acts as an acid with OH minus its conjugate base. Substances that can act either as acid or bases are called as amphoteric substances. Strong acids versus strong bases. Strong acids are more readily release H plus into water. They more fully dissociate. For example, H2SO4 is an example of a strong acid where H2SO4 dissociates into 2H plus SO4 minus. Strong bases more readily release OH minus into water. They more fully dissociate. NaOH dissociates into OH minus and Na plus. So for any acid to describe its reaction in water, it's shown here. This equation describes the expression where K often denotes Ka or Kb for acids or bases. K is equal to concentration of A into H plus divided by H into A. So this equation describes the dissociation. So strength of an acid or base is then related to the dissociation constant K, strong acid or strong base, where pK is equal to negative logarithm of K as before. Lower pK is equal to stronger acid or base. So lots of reactions are acid-base reactions in the environment. Huge effects on the solubility due to this most process. So with this we will stop this lecture here. In the next